Think about it. We are constantly surrounded by these incredible structures, skyscrapers, bridges, airplanes, and they're all held together by welding. But how do we know those connections are safe? Today, we're going to dive into the rigorous and honestly pretty surprising science that builds our trust in the welds that hold our world together. I mean, everything from massive steel bridges to the critical components inside a jet engine, they're all serving a vital function under incredible loads. The process of making them, fusing metal together with this intense, focused heat, is as high stakes as it gets. And you can imagine, with a skyscraper or a plane, there is just zero room for error. You see, a weld isn't just like gluing two pieces of metal together. No, it's this incredibly complex, almost chaotic zone where everything changes. The intense heat literally transforms the metal's internal structure, creating a brand new hybrid material that's totally different from the original metal and the filler that was used to join them. And that brings us right to the big question, doesn't it? How in the world can we trust this tiny sliver of metallurgical chaos? How do engineers actually prove that it's strong enough and durable enough for the job? Well, the answer is testing, and not just any testing, rigorous, destructive, and honestly pretty clever testing. Okay, so let's get into the fundamental challenge that every single welded joint presents. We call it the welder's dilemma, and it all starts with understanding what a weld is actually made of. A weldment isn't just one thing. It's actually three distinct zones, all sandwiched together. First, you've got the original base metal on either side that wasn't really affected. Then you have the new weld metal right in the middle. And then there's this critical area in between called the heat-affected zone, or haze for short. The haze is where the original metal got super hot but didn't actually melt, and its properties can be the most unpredictable part of the whole joint. So, to solve this whole dilemma, engineers basically ask three big questions. And the first one is the most obvious one you'd think of. Is this thing strong enough to resist being pulled apart? And to answer that question, you need the most fundamental test there is, the tension test. Its purpose is brutally simple. Find out exactly how much direct pulling force a weld can take before it snaps. So what they do is pretty straightforward but kind of brutal. They take the super precisely machined sample of the weld, lock it into a powerful machine, and then they just pull it apart. It's a destructive, one-way trip designed to find the absolute breaking point of that material. Now here's the cool part. While the machine is pulling, it's actually drawing a graph called the stress-strain curve. You should think of it like an EKG for the weld. It shows us exactly how the material stretches and resists that force from the very first little bit of give all the way to the moment it completely fails. And that graph gives us the one magic number we're really looking for, the ultimate tensile strength, or UTS. That's the very peak of the curve, the absolute maximum stress the weld could handle before it started to fail. That single number is a cornerstone for all kinds of engineering designs and safety codes. But look, strength isn't everything. A material can be super strong, but also brittle. A weld that can handle a slow pull might just shatter from a sudden impact. So the second crucial question is it tough? And you really got to get the difference between strength and toughness, because they're not the same thing at all. As you can see here, strength is like winning a slow, steady game of tug-of-war. Toughness? That's more like taking a sledgehammer blow and not shattering into a million pieces. You can be strong but not tough, and vice versa. So one way to start gauging toughness is by checking a weld's ductility, which is really just a fancy word for its flexibility. The bend test does exactly that. They take a sample of the weld and literally bend it into a tight U-shape. If it can make that bend without showing any cracks, it's a great sign that the weld is sound and can handle being deformed under stress. But if you really want to know how it'll handle a sudden shock, especially when it's freezing cold and metals get more brittle, that's when engineers bring out the big guns, the Charpy V-notch test. This is pretty much the gold standard for impact toughness. And this test is seriously dramatic. They take a small, notched bar of the weld metal, cool it way down to a specific temperature, and then, wham, a giant, heavy pendulum swings down and just shatters it in one go. By measuring exactly how much that pendulum slows down after breaking the sample, they can calculate precisely how much energy the material absorbed. The more energy absorbed, the tougher the material is. Okay, so a weld can be strong and it can be tough. But that's just a snapshot in time, right? What about over a lifetime? A bridge or an airplane wing has to endure millions and millions of small stresses. And that leads us to our third and maybe most important question. Will it last? This is all about the danger of something called fatigue failure. And you've actually seen this yourself. You know, when you take a paperclip and bend it back and forth, and eventually it just snaps? That's fatigue. It's when millions of tiny, repetitive stresses, none of them strong enough to break the weld on their own, add up over time and cause a sudden, catastrophic failure. So that leads to a really interesting question, and I want you to think about this for a second. When it comes to a weld's fatigue life, enduring millions of those little cycles, what do you think matters more? The raw brute strength of the steel itself, or the physical shape and finish of the weld? Well, the answer might surprise you, and it's one of the most fundamental rules in all of weld design. Geometry is king. Yeah, you heard that right. Let me show you what I mean. Get this, a really smooth, carefully shaped weld made on weaker steel will often outlast a lumpy, rough weld made on super strong steel. Now, why on earth would that be? It's because every sharp edge, every little ripple in that rough weld acts as a stress concentrator. It's a tiny point where all the force of every cycle gets magnified, giving a fatigue crack the absolute perfect place to start growing. Okay, so after we've pulled it, bent it, and smashed it with a hammer, and considered its shape, we can finally start to get a clearer picture. We can arrive at the final verdict on the health and reliability of that welded joint. And what you realize is that no one test can tell you the whole story. To really trust a weld, it needs a complete health check. It has to prove its brute strength, its flexibility, its toughness against a sudden impact, and its durability to survive that long, slow grind of fatigue. You know, there's a quote from the source material that just nails it. It says that testing like this is the essential bridge between what designers think will happen on a computer screen and what actually happens in the real world. It's what turns theory into a safe, reliable structure. So at the end of the day, our world is kind of built on trust, right? We trust the bridge will hold. But engineering is built on proof. And it really makes you think. What else do we just take for granted every single day that's being tested just as rigorously, hidden away behind the scenes?